The theme of the first part of what I'm going to speak about, which is why I got to where I am using 3D technology, and why it's been the best way to define what my life has been about is three-dimensional visualization. And the transition that I personally made from loving 3D design to then wanting to be able to create 3D applications, at some point you realize no matter what tools are out there, you're going to have to learn how to do some code. So there's a crossing point there, and that's actually what informed the desire to make an immersive development environment, a way to actually interact with code in a three-dimensional way. This one, Raydream 3D, my uncle sent me this software package when I was 10, and because he sort of recognized I'd been doing these drawings, and he said, you know, I think you might like this 3D software. You might really enjoy it. Because the basic principle there is that you're making a sketch, and then you're extruding that sketch through three-dimensional space. And so in your mind, you can sort of imagine what that looks like to pull a circle through space, and you get a tube. So it's just a lot of fun when you're a kid to be able to be given a tool like that, because then your imagination starts running, and you start building whatever you can think of. I ended up working at an engineering shop at the local university when I was in high school. And so we're jumping 10 years, and then that rendering there, it's from a little bit more of a recent version of the package, but I do like to show the contrast of what a tube looked like in 1990 versus, let's say, 14 years later. It's just amazing to see that sort of brushing on the material. The key concept that I want to communicate here, and I'm going to use this diagram to illustrate this. So first of all, we have that same sketch concept that's in the basic software, where you're drawing shapes and then you're defining those shapes using functions. You're actually saying that the radius of one of those circles is equivalent to the other radiuses. So you can actually set very nice little repeating patterns where you only have to define one element, and then it repeats itself to other elements, and then those can then build into larger structures. So that's a programming concept that I see as a functional declarative concept. And then on the right-hand side, this is a supercharger for a car. Even if you're not familiar with how a supercharger works, what I want you to do here is just imagine in your mind for a second. So you see that belt on the upper right. So if you turn that belt, or if you turn that knob, imagine the sequence of events that follow when you take that action. So you turn, and then we can sort of, in our minds, we can see the belt pulling that central shaft there, and then that starts rotating that set of fan blades. And then naturally you think, well, okay, if I'm rotating the fan blades, that's going to start drawing air in that direction. Then we can see, where's that coming from? It's coming up the tube, and then there's that filter at the top. So by, in your mind, rotating that crank on the far end, there's this chain of events that happens, which actually involves 3 or 4 other sort of major components that are all working with each other. To ultimately, in the case of a supercharger, you're drawing air and compressing it so that there's a richer mix inside of the engine, so that you have a more powerful output. And then you can keep diving in just with the visual graphic. You can see how the density actually increases in the blades as they get deeper into the tube. And the result there is when the air is actually trying to fit through there, it's getting compressed because there's tighter spaces that it has to fit through. And then you can see some oil tubes running to different parts of the shafts. And you just imagine there's just all these little built-in little tools. And now think about how modern software works, and how you have so many little components that are all working together to add up to some greater function. There's an analogy to be made here between something that's physical, that has a physical function, and then software, which also has a function that relies on many different parts working together. But the point here is that with this 3D model, I can actually grab that shaft. I don't have the program, but if we were in the program, we'd grab that and turn it, and you could actually rotate this whole mechanism and see the process. And that's something that your mind can grasp and really appreciate the mechanism. So the way I applied this, I was working in this engineering shop. We were building microsatellites. This was at the Colorado Space Grant Consortium at the University of Colorado Boulder. Then also I was working at a planetarium at the time too. Kids would come up afterwards, and they actually thought they had gone to space. And I remember feeling that in the back of my mind too when I was that age. When you're in a dome and there's stars being projected around you, you really do feel that you're transported somewhere. And that speaks to the power of immersion, and how if you put your consciousness in an environment where you're feeling like you're transported somewhere, you start absorbing information. I say like a very high bandwidth kind of way. There's really nothing interfering the data from just getting into your mind and you conceptualizing something. So these were two things early on that I felt I didn't really see how they were related, but they ended up being related later in life. By the time I went away to school, this was the second really powerful experience I had in terms of immersion, which was going into a cave environment. This is before the prevalence of modern VR. It used to be that you would have to go into a room like this that was powered by supercomputers that would actually render images on walls, and then you'd wear these polarized glasses that would rapidly change, synchronized with the images that are projected on the wall, to give your left eye and your right eye some stereoscopy. And I remember seeing this for the first time, and there was an engineering student who had ported Doom 3D into this cave environment as like a side project, even though it was supposed to be used for like scientific research. And I just remember walking down a three-dimensional hallway in Doom. I didn't even do any like of the game, like, but I just remember walking on a hall, and then I actually also fell off a ledge into a pit of lava, and you just feel the walls rushing past, and you get this sense of motion, which is like powerful. First job I had was working at a solar company, and what you're seeing here is this is a lens that has prisms etched into it. I'm just illustrating this example because it really kind of sparked my imagination when we built these lenses, because you see here there's this graphic of these prisms, and there are these light rays that are shining between each one of those points on the prism. And in order to generate that model, there's actually a little macro algorithm that runs that you can actually watch the sunlight coming in and then adjust the angle on the lens. And then there's a target objective function, which is to focus that point somewhere on a grid. And I remember watching the computer actually solving this problem in like in sort of a slowed down time frame where you could actually see each ray of light etching this model. Just being able to play back some kind of algorithm in a slower amount of time so you can really wrap your mind around it. I always really thought that was a great way to learn something. Okay, so here's where I really hit the wall in terms of programming, and that's when I actually got to business school. When I got to Stanford, I'd sort of seen California as this tech mecca. I'd never lived here. And I was expecting to go into the classroom, and it was an intro economics class. And I had this vision in my mind that we were going to be using some kind of tablet where we're going to have graphs, and the professor was going to draw something and then manipulate it with his hands and like be able to show how the supply-demand curve works. And to my horror, he got out the whiteboard markers and started drawing on the board. And I thought, like, God, this wasn't what I was expecting. It didn't match. I thought we were living in the future here. What was worse, though, was that this class of very impatient MBA students, and I'll tell you that's the most unifying quality of an MBA student, is that they really expect like everything to be given to them, and I'm speaking as one. And this story I think illustrates that. But I just remember the look on everyone's face, because in order to do the supply-demand curve, you actually have to do calculus to determine where the inflection points are on the curve, so you can actually optimize where to set a price, let's say, for a product. And just like everybody had taken calculus at some point, but not applied it in any way, or certainly appreciate what calculus, how it works. And so at this point, I thought, I'm going to go home and I'm just going to program a supply-demand curve, and just have a line and have a box underneath the line, and then be able to adjust the curve and have the box grow and shrink depending on how steep the curve is and where I set the price point. And the nice thing about that is the bigger the box gets, the more money is inside of the box. And that's a very easy concept for an MBA to appreciate. Okay, but then the problem was, now what do I do? How do I actually program this? So I built this little set of programming tools because it started with the supply-demand curve, but then quickly became more of a, my interest became more of like how to actually visualize computer code. So what I'm going to show here is just this little simple addition problem. So what this algorithm does is it takes the number 2 and 3, turns it into a little stack of binary bits, and then physically pushes them into each other. And if you have a collision with two bits that are on, they carry to the next bit. So there's this little, again, you can imagine this physical process of pushing these elements together. So basically, you break 4 times 4, 4 times 3, and then 4 times 2 and 4 times 1 for the decompose. So you get the concept here of how basically like you can physically, mechanically break these elements apart and then sum them back together into a solution. So this is where I had to go and really to be able to understand this. So in this case, what we're going to do is we're going to ask this algorithm to seed a public and private encryption key. And the way it does that is it's using a prime number generator, which is this part, which is depending on a Miller-Rabin primality test to actually test the primality of randomly generated numbers, which you need to build an encryption key. And so what you're seeing here is there on the ground floor, there's sort of like the skeleton of what the program is defined as. And then as the functions are instantiated, they build these little stacks. And each stack might call other functions that then continue to stack. And you see, just if your eye just follows that little bit that's flashing around the screen, that's just functions passing data back and forth to each other, parameters. And eventually you see the stacks grow and shrink and grow and shrink. And eventually you land on a prime number that you can use, a large prime number for the encryption algorithm. And then that eventually makes itself all the way back to the public key, which is being generated. So this was the first step for being able to start to visualize what an algorithm might look like in a way that isn't just flow diagrams, which is generally what you see with graphical programming languages. We wanted to take it a little bit further and actually show some animation here. Fred Brooks wrote this back in 1986. The structures of software remain inherently unvisualizable, thus depriving the mind of its most powerful conceptual tools. This lack not only impedes the process of design with one mind, it severely hinders communication among minds. So we are using visualization as a communication tool more than we're using it as an actual individual programming tool where you're building functions. Now, as interesting as that concept is, and that's actually where we'd like to get to and where we see the future of software, right now, today, big part of software development every day is reading other people's code and trying to review other people's code and understand other people's code so that you can actually use it in a productive way. So with virtual reality, we've been given this really amazing platform to be able to do data visualization in a way where you can display lots and lots of data in an almost unlimited space, kind of like a planetarium. But it's also this tool to communicate in a way that we haven't had before. For our tool, which I'm gonna switch on here and I'll finish with that, we have three categories that we focus on. One is for walkthroughs. So when somebody's onboarded to a project, it usually takes many months before they're actually productively creating code and contributing. And so that's a huge cost for any organization because it's just a lot of time invested there. So we can actually speed that up through virtual reality training. You remember more of what you see in virtual reality too. If I asked all of you, you would be able to remember your way how to get out of this conference center if you had to, even without even thinking about it or taking notes. You have some sense of how you got here. So spatial memory is actually an evolutionary mechanism that's built into our minds. With code review, we can look at how just visually how individual modules or classes are actually tied to other classes. And if I change something in one class, how does that change actually percolate and sort of affect the rest of the code base? So that's something I love to show. And then finally, in terms of debugging, we can do something that's really unique, which is just like what I was showing with that little RSA algorithm, the animation. We can actually animate a Java system and actually show threads and objects and data getting passed around the system. And I haven't really seen another tool. There's lots of debugging tools out there that are very powerful and actually can do more than what we can do in terms of giving you rich data. But in terms of actually displaying the entire heap of the JVM and being able to look at all the threads, you do need a lot of space to lay out that kind of visual information. And virtual reality just lends itself very well to that. So in this environment, I have on the floor here in front of me a map of a Java project. So we see this directory structure that's sort of fanning out from the central node. And each one of these packages contains a vertical stack of classes that are contained inside of that scope. So what I can do is I can open one of these, and I'm exploring this as a three-dimensional set of files where I have these four classes in front of me. I'm going to go down to this class because if you notice, this one's actually very visually complex. There's a lot of geometry associated with it. And then we're going to open this class, and now what I'm seeing here, horizontally across the top are all those state values. And then vertically we have the methods. And I want to show here, this is the initializer method. And you can see, if you see it from my perspective, this stack that I'm looking at is actually about 30 feet tall. So it's kind of like the Star Wars scroll. It just goes on and on. And the thing, it's nice in VR to be able to display something like that, but it's also kind of frustrating to see, like, it makes sense, you write an initializer and fine, it does everything to set up the program. But it would be great to break this up into chunks. But what we can actually do is I mentioned the dependency lookups. So I'm going to push a button here, and if you see, there's all these yellow dots that fly around all over the room. And each one of those is a dependency that this method is calling out to. So I can actually visually see that initializer interacts with all the front-end modules. So we have a view module here. I have a model module. There's one call into the utilities. Something's reading from a file somewhere. There's user interface, and then there's actions. So those are all mostly front-end. There are a few middle and back-end parts of the code. This is the first order method calls. And then if I go to the second order method calls, then I'm seeing back here in the database, I'm starting to see some classes light up back there. And then further, if I go to the third level and the fourth level, I'm really seeing a lot of activity back there. So this actually, just by starting the initializer and graphing this, I can see what the separation is in this project between the front end and the back end. And just visually, that's helpful, and conceptually, that's helpful for me to be able to differentiate there. And then, as I mentioned, we can also trace this code. So I'm going to start running the execution environment. And what I see on the wall here in front of me, stretching out also about 15 feet long, is this timeline. And this is just showing, as we trace on the JVM, this is pre-recorded. So I have all the actions that are taken when we execute the program. And then they're broken into these individual phases, which you can actually start to infer some kind of visual pattern here in terms of loops and different phases of initialization that are going through here. And I'm going to start playing this animation. What you're going to see here is on the floor are the static classes, and then the instantiated objects get added to this tree that grows out of the ground. And that red line is representing one of the JVM threads that's spawning these objects and reading and writing data to different addresses. So I'm actually, as the timeline advances on the chart, we're watching a slice at every point in time in the JVM. The entire heap is displayed here in front of us. And I can actually see objects getting garbage collected or added, or just threads writing to them. And that's something that I'm going to jump forward later on here. Again, I'm looking up here, and now these stacks are about 60 feet tall. I have all of the objects in memory in these large arrays. And for a very sophisticated like enterprise code base, we see this all the time where we have these big arrays and many threads reading and writing to all these different points. It's just very powerful to be able to visualize that. I'm going to show two more quick examples. One is a multi-thread application. So this that one we were just looking at was a single thread. This one has 4 threads. Much simpler little code base, but it's fun to see these threads interacting with each other. So I see the blue is instantiating the basic structure of the model. And then we have red, green, and yellow are the other 3 threads. The yellow is an event processor. The green and the red are adding events to a queue. And what I can see here is that there's this one object in the back, the event queue. And that's the one object in the system that actually has multiple threads interacting with it at any given time. And the original version of this code, when we looked at it with the developer who wrote it, they'd actually programmed it in a way they didn't realize wasn't thread safe. So at some point, the yellow and the green thread, and also the yellow and the red thread, were both reading and writing to the same function at the same time. Now notice here that the red and the yellow are actually split between 2 functions. They're interacting with this object at the same time, but the function is actually split into a put and a take method. And that therefore precludes any kind of race condition from evolving there. So just by it was amazing when we looked at this, because it was immediately obvious. It was immediately obvious that when our eye is actually drawn to that crossing, we pay attention to it and we say this might not be thread safe. Finally, I will show. I'm going to load Elasticsearch here, which if some of you in the room are maybe familiar with this, Elastic is they're based in Mountain View, distributed team. Elasticsearch is their search engine tool for enterprise databases, and it's close to 1 million lines of code. So a very, very big code base, very well broken up into interdependent components. But we can see here in this big graph, and again, to give a sense of scale, this graph is as large as the room that we're in right now. At least in that direction, it goes more than 100 feet. So this automatically lays out into this big space, and I can then start to form a model in my mind of this central module that I'm looking at, which is the main module. And then there's three important modules that I'm aware of that when I talk to people at Elastic, and when you look at this code base, that they say are important. One is the indexing module. The other is the search module. And then in the back here, we have all of the common sort of utility functions that end up getting accessed a lot. So these sort of three neighborhoods, you can see how they're split apart, and then each one has its own set of functions that are sort of scoped to the package. And forming a model in your mind of that is very it's very unforgettable. It's something that you can close your eyes and actually imagine in your head. And if you're having a conversation with somebody who's somewhere else in the world, or maybe there's 2 or 3 teams that are all, or there's 2 or 3 developers that are in different offices, going into this environment, actually being able to walk somebody through those different packages is a great way to just synchronize your understanding very quickly. And this is where we see the future of where software is actually going to go, is in a more collaborative, immersive direction. That's at least our belief. If you asked machine learning people, maybe programs will be writing programs in the future and we'll be more hands-off. But even then, it might be helpful to have a visual interface to actually understand the machine better. So with that, I would love to see what you guys think, and we can do questions, and then also anybody who wants to try it is welcome to actually come up on stage and put the headset on. So be happy to hear your thoughts about what we're doing here at Primitive. Thank you.
Do you have a question? Oh, here we go.
Yeah, you just blew my mind. Thank you very much. It looks promising for analyzing and understanding the code and what's happening. Have you considered if some kind of software creation, like programming, actually could happen in VR, and what the input method for that would be?
So the last word there, input method, I think is critical, because with virtual reality, one of the big hang-ups right now is what's the natural way, what's the equivalent of tapping on a screen? What's the equivalent of a keyboard? The keyboard part is actually the most frustrating part, because I'm sure if you've ever tried to log in on your TV and you're using the remote, how horrible that is. But and nobody's come up with a better way to do it other than actually connecting a keyboard to your TV, which who's going to do that? So that's actually a big problem, is the input. How do you actually, if you're still programming in text, which I actually think that is going to be the way that we continue to program for forever. I think that it's just how we do it, and it's like the English language. We're not just going to give that up. So a keyboard is a critical piece of that, and there are some virtual keyboards that are actually pretty cool that track your hands, but it's not there yet, and that's a big holdup. But I think you were also alluding to the idea that you could actually construct a program not using words, but using more like building blocks. And that's, I think, a great idea that's been explored in other, and when you, I actually did do Lego Mindstorms was one of my first programming languages, I would say. They actually have you build blocks, and that's also like Scratch. There's programming tools for teaching kids. I think that's great too, and you could imagine maybe on a higher level, plugging libraries into each other, sort of wiring them up using your hands. That would be I think really profound. But the input is the big, I see as the big hurdle to get over there, to actually making it so you could have a true development environment that you're building inside of.
All right, just right here.
Thank you. So I'm a visual person, and I think most of us in IT are more analytical and visual, right? So I totally love this, and this looks like in a future world. So I'm thinking like, for example, while explaining the architectural design, like you're in a service mesh and you want to explain to your team, this would be wonderful, like because teams sometimes work in silo and they only know their part, and you want to take it all the way from load balancer till the backend enterprise resources and stuff like that. So is this a product, or is it like a software, or based on the needs we can develop? What is this about?
And I wanted to shy away from just giving a straight product pitch, even though that's like naturally what you want to do as an entrepreneur. But the answer is yes. So this is actually something that you can download on Steam for free and try it out. We have demo code bases bundled into it. We also have tools for IntelliJ and for Visual Studio that actually automatically turn your project into a three-dimensional map. So no other steps required. You're just installing a plugin and running it, and then it generates this map for you to look at. And it also works in 2D, so you don't have to have a VR headset. You can actually fly through it like it's like a first-person shooter. But just speaking more generally to the point, and I did want to like not just give a product pitch here, but the idea of so in enterprise code, and we work with a lot of enterprises. We're actually commercially available as well. I get the opportunity to go into a lot as a sort of outside consultant, get to go in and see these software architectures that people are wrestling with every day. And people talk about this in conferences and what the challenges are, but it always amazes me, and this is just purely a function of how organizations work, how you can have one team dedicated to one piece of some software architecture. You can have another team somewhere else that's working on the exact same problem, and they're completely unaware of each other. And then that you sort of riff on that idea too. You could have a team that already solved the problem that the other team comes along, they're completely unaware of, and then they end up repeating the work. They don't even have to be doing it at the same time. Or you can have situations where both people are solving the same problem, and then they end up those interfere with each other. So there's so many cases where if you can help people to just be aware of what the overall lay of the landscape looks like, it's just better for the organization. Communication is the key thing there, and really all I'm saying is that virtual reality is this more powerful, high bandwidth way of communicating to people, which I think is very exciting.
Any other questions? I'll take right here.
Hi. Is there a code base size or complexity level that you think works best for this approach? Like at some point, you're going to have like some enormous ball of mud that is like it's incomprehensible in text. It will be even more incomprehensible in VR.
Yeah.
But then there's a sweet spot somewhere where VR you see like, okay, like this domain is clearly here. It clearly talks to this domain, and the domains are of reasonable size, where you don't look at it and say, oh my god, like.
I'm laughing to myself right now because you just made me remember. So we've looked at. I'd say on the larger the better, generally speaking, and that's because I showed you that little small code base, and that's kind of it's cute, right? Like it's sort of, it wouldn't take you too long, alternatively, just to read through the README, let's say, and kind of find your way through it. Even though we do see still there's value there. But the more you scale it, the more you it becomes impossible to be. If you open something in your IDE like Elasticsearch and you're diving through the folders, you could actually be doing that for months and you wouldn't touch like the whole architecture. And it might take you a while to really form a model in your mind. So the bigger the better generally. But it's funny because the largest project we've ever looked at, we've looked at like 7 million line code bases, and that's fine. We just lay it out in a big space. But the funny ones, there's one that we looked at that was crazy, and I don't know if I want to say what company this was, but it was IBM, and they'd be fine with this too because they were laughing about it too. And we were at a conference and we downloaded Open Liberty, which is this massive code base, and it's not just big in terms of lines of code, but there are these like really, really dense classes, like these like classes that have just they're like God classes that just handle all this data. And you saw how we graph it, where we create these little balls and sort of lay things out. And at some point, like we're loading the model, and it's a graphics program, so it's taking a while to load. It's like, wow, this is taking a really long time. And finally it renders, and it was just this like hurricane of like spaghetti is what it looked like. And it was great actually to show the team that, because they saw this and like, yeah, we know our code is really cumbersome. Like it's hard, and it's painful. It takes 10 times longer to debug something because it actually takes longer to compile and longer, like you can't break it down. So seeing it as a graph actually furthers that case. And I think that if anything, it's just going to show you, yes, that's something that we really should actually prioritize and refactor. But it's funny because we actually hit a graphical limit at some point. We're just drawing that many vertices to like illustrate all the different methods and how they're connected together. It actually almost broke the system. So that's why I was laughing when you said that, because that was the first thing that I remembered.
Any other questions? Nope. Take over there first.
As a spatial thinker, I really love this idea, and I really want to start programming in these kind of environments. What I'm concerned is about the gorilla arms. With that, it might be a following up question about of the input method, but think about long-term activities, like when you program for hours and hours and hours. If you have that method, even without the keyboards, even when you have those libraries and building blocks that's sufficient for your application, you end up having your arms so exhausted as a gorilla kind of. What are those input methods that you are planning or imagining for
Totally.
the future coming up?
So first, I think it bears mentioning the sort of where we are with virtual reality right now in terms of these discomfort levels that people have. So one is that a lot of people get motion sick, and in VR experiences where you move around a lot, that's especially bad. We keep everybody planted in one place to avoid that as much as possible. But still, there's actually, ask me later, but there's a really interesting reason why we get motion sick. And you all probably know it's because of your inner ear and your eye mismatching. But there's actually an evolutionary explanation having to do with poisonous berries. That's the reason for that. Motion sickness is one part of it. Neck strain. These headsets are still, they're if you hold it, it's sort of lightweight. But when you wear something on your head that has some weight to it, I get neck strain after a long period of time. That's actually my biggest complaint with it. In terms of the interface, everything I said about, we still need solutions they just feel more natural, that you don't have to be necessarily holding something at arm's length and waving your hands around because you get tired very quickly. Turns out that like using a mouse and keyboard, you could do that all day. We all do it all day, and it's not hard. Of course, I get repetitive stress injury. I have RSI in my hand, and I like being able to put the mouse down for a while, or just not use the mouse at all. So I think keyboards are critical for this. There's one other thing I was going to say about that too. Only that when we do these collaborative sessions, they usually, like, the excitement tends to overcome the pain. So we actually do hour-long, 2-hour-long sessions with developers, because once you get into your own code and you start talking through it, and discovering, like seeing it in ways that you didn't see it before, there's actually an element of excitement. That's actually my favorite part about what we do, is when we get a team in this, and they're actually, for the first time, they're like, oh my God, I understand your code, I get it, right? And that excitement actually leads to longer sessions, which I think is a nice byproduct, overcomes the other discomforts.
So we're at session time, but since it's just lunch, I've offered John to stay up here so that anyone who's interested can kind of go in there and check it out for a little bit. But open it up for questions. Just come up to John now, because I don't want to keep you all from lunch. But can I get another round of applause for John?
Thank you guys.
And thank you all for coming.
Thanks so much.